Hello, this is Geometry Chapter 2, Section 4, Deductive Reasoning. And again, apologize for the last video being really long. Hopefully this one won't be as long. But a lot of writing, so here we go. Deductive reasoning is different from inductive reasoning. We talked about inductive reasoning early on in the year. Inductive reasoning is when you make assumptions or draw conclusions based on observations and patterns. But deductive reasoning requires more than that. For deductive reasoning, you need to actually have facts and rules and properties in order to make conclusions and make assumptions. So the first example we have here is basically asking us to determine whether each conclusion made is based on inductive or deductive reasoning. So again, in inductive, we're looking for observations, patterns. In deductive, we're looking for facts and stuff and rules and stuff like that. So, A, every time Katie has worn her favorite socks to a softball game, she has gotten at least one hit. Katie's wearing her favorite socks to a game tonight, so she would conclude that she will get at least one hit. Now, because this is talking about patterns, observations, it says every time Katie has worn her favorite socks, so she's worn it several times. That's an observation, a pattern. Then part A, we know that this conclusion is made off of inductive reasoning. All right. B, if John is late making his car insurance payment, he will be assessed a late fee of $50. That is a fact, okay? John's payment is late this month, so he concludes that he will be assessed a late fee of $50 because this is not based on pattern. It's not like he's not making this conclusion because he's made his payment late so many times. He's making this conclusion because he was told that if he was late, he would be assessed a late fee. So this is deductive. Deductive reasoning for part B. So now we're going to let you do this example here and again determine whether or not it's deductive or inductive reasoning that's taking place. All right? Now, the next thing we want to talk about is we said earlier that deductive reasoning requires using rules and facts and that kind of thing. We have two main rules, if you will, laws for deductive reasoning, and the first one is this one here, law of detachment. And what I have done is made kind of like what the rule is here on the left, and then provided you with an example off to the right. So first of all, there are basically three parts to this law, and it is an if-then statement. So the if part is that there are two pieces to the if. It means that these two things have to happen first, and if these two things happen, then we know that this last thing is true, okay, or is the conclusion that we can draw. Okay, so that might sound kind of confusing, but hopefully once the example gets there, you'll understand what that means. So the first thing has to happen. You have a conditional. P implies Q. The conditional needs to be true. It needs to be a true conditional. So over here we have, if a car is out of gas, then it will not start. That is a true conditional. Okay? Then the second part comes. P has to be true. Okay? So there are always going to be two parts to the law of attachment here. Okay? First, they'll give you a conditional. Usually the conditional will be given to you in a very generic sense. A car. We don't know whose car, what car. It's a car. It's a very general way of stating it. But in the second part, they're going to be very specific most of the time. So now we're talking about Sarah's car. But again, because we're talking about a car being out of gas, that was the hypothesis, car out of gas. Same color here, if you can see that, okay? So the first statement is a true conditional. And then the second statement is going to be a specific statement that refers to P. It refers to the original hypothesis. So a car is out of gas, Sarah's car is out of gas. If these two things happen, then the logical conclusion is that Sarah's car will not start. All right, so two pieces. P implies Q is true, P is true, and if these two things happen, then the logical conclusion is that Q is true. Okay, so now we want to go and see if you have any success here. Make sure I cover that, okay? All right, so remember, we're looking for that model, the two-step process, okay? So here we go, example 2. Determine whether each conclusion is valid based on the given information, if not right, invalid, and explain your reasoning. So here we go. here is my first statement, and again, we talked about this before. The first statement is usually very general. If two angles, we don't know the angles' names, they're just two angles, form a linear pair, then their non-common sides are opposite rays. Okay, so if two angles form a linear pair, then their non-common sides. You have a diagram over here. When they say non-common sides, this side right here, we have two angles here. This side right here is the common side. They both share that side. So the non-common sides are going to be this side and this side. So those are going to be opposite rays. So that's a true conditional. That's the first part that we need. The second part that we need is a statement that is talking about a specific hypothesis. So if two angles form a linear pair, that's generic. Here we have angle AED and angle AEB. Those are specific angles, and they form a linear pair. So this is a hypothesis in general form. This is a hypothesis in specific form. So this follows the right pattern. So the conclusion should be that the non-common sides, which in this case are ED and EB, are opposite rays. So this conclusion is valid. And we can say here, valid. All right, so hopefully that made sense to you. We are going to try another one here, a little less mathy, if you will. So now we're going to say, here's the first statement. If mica, and so this is one where you'll notice that it's not generic, okay, but that's okay. It isn't always generic. It's just usually generic. So the first one says, if mica goes to the beach, so that's our hypothesis, our P. If mica goes to the beach, then she will wear sunscreen. Okay, so our conclusion is wearing sunscreen. Okay, you can't really see that yellow, so okay. It doesn't like, okay, there we go, Q. So if mica goes to the beach, then she will wear sunscreen. The second statement is mica is wearing sunscreen. So this second statement is referring to sunscreen, which is not part of the hypothesis. It's actually part of the conclusion. So this is actually, P implies Q is a true conditional. It satisfies the first part of the requirement. But the second statement is supposed to refer to the hypothesis. And in this case, it's referring to the conclusion. Okay? So that's already the wrong setup. So their conclusion is that mica is at the beach. Again, mica is at the beach is P. Remember that before, we know that P implies Q. We're supposed to have P is true, and then our conclusion is that Q is true. So this is not the right format at all. This is invalid. Okay, so we have that it is invalid, and as far as our reasoning, it's not following the right format. The given statement that mica is wearing sunscreen satisfies the conclusion of the conditional instead of the hypothesis. So that's not going to be true. So that one was invalid. I'm just trying to follow along here. So you can write all that out. I don't really feel like writing it up. Basically, it doesn't follow the right pattern. This is the wrong statement. We should have a statement here about mica going to the beach. And we don't. So there we go. And so now we have a couple for you to do. Do it yourselves, part A and B. So again, determine whether it's valid or not. If it's not invalid, write invalid, and then explain why. Usually because it doesn't follow the right format. Okay? So, all right. The next thing we want to do is we can also explain ourselves instead of having to explain like a whole written verbal description. You can explain things by using a Venn diagram. So I have both the example and the do-it-yourself on the same page. So remember that for this do-it-yourself, it'll have the same directions as example 3. But here we go. We have if a primate is an ape. So this is our hypothesis. P here. If a primate is an ape, then it does not have a tail. And there's Q. All right? And so then our second statement is Coco is a primate who does not have a tail. So as you can see, this is going to be invalid already because this second statement is talking to us about not having a tail, which is Q. All right? In order for it to be law of detachment, we should have something like Coco is an ape. Okay? Or whatever, but it doesn't say that. So this is based on Q. So P implies Q, and Q do not have any valid arguments, okay? So the conclusion Coco is an ape is invalid. But more importantly is how do we show that with the Venn diagram? So what I have here in the first diagram is just kind of showing you what the first conditional is saying. If you are a primate, so we have this big box here, all inclusive is all primates. And then inside of it you have two types of primates. You have apes, and then you have primates with tails. Okay? So if you're an ape, then you do not have a tail, so there's no overlap there. So that's what we're showing there. And then, as far as over here, we actually have two things, or two possibilities that Coco could be. And this is how you could demonstrate that this is not valid, okay? Because according to the second part, Coco is a primate, so Coco is inside of the primate square. So this dot here is inside of the primate square, and so is this dot inside of the primate square. But it also says does not have a tail. So this dot is inside the primate square, but not inside the with tails. Also, this dot is inside the primate square, and also not inside the circle with tails. So Coco could be in either one of these places. But the conclusion says that Coco is an ape. So the conclusion is that Coco would have to be in the ape circle. But clearly you could be out here and be a primate who's not an ape that happens to have no tail. So that is how you can show with the Venn diagram that the conclusion is invalid. All right, so this little guy we want to put over here, definitely invalid. Invalid. And then I'm going to close this off for you real quick so that you can see all of that. It kind of got to the bottom of the screen there, but we have the do-it-yourself on the bottom there. And then we're going to go to our second law, and hopefully we can bring back, we need to bring back my my little board thing down here, my little strip. Okay, our second law is the law of syllogism. And I don't know why, but I started calling this the law of silly goose a long time ago. Probably just because it sounds cool, law of silly goose. But it's the law of syllogism. And the law of syllogism is also going to have two parts. And so if, and I forgot my Venn, so sad. And again, we've tried to provide you with the symbolic representation, but also like an example to kind of help you see what's going on. But for this guy, you have two conditionals. You'll remember that the law of detachment had one conditional, P implies Q, and then number two wasn't a conditional. It didn't have an arrow. It was just P is true. Okay, it was a statement. And then the answer was a statement. The conclusion was that Q is true. But in this case, you have two conditionals, and your answer or your conclusion is also another conditional. They're all arrows, all conditionals, okay? So first, you have P implies Q is true. Second requirement is that Q implies R is true. And if that happens, our conclusion is that P implies R. Okay? So basically what's happening is you're getting rid of the middleman. It's kind of almost like the transitive property. P goes to Q, Q goes to R, so let's just get rid of Q and go from P to R. That's kind of what's happening. So I want to be very clear that these two statements do not have to be in this particular order. You could have had a Q implies R and then P implies Q second. That wouldn't have mattered. What you have to look for is that the conclusion of one statement, which is in this case Q, is the hypothesis of the other. So the conclusion of the first statement is the hypothesis of the other statement. That has to happen. And then if that happens, then of course our conclusion is that P implies R. So here we have an example. If you get a job, then you will earn money. And then if in turn you earn money, then you will buy a car. So what we're doing is we're going to get rid of the middleman, which is earning money. And our conclusion is that if you get a job, then you will buy a car. So that's kind of how the law of syllogism works. But again, it has to be in that format. The conclusion of one statement has to be the hypothesis of the other. And so we're going to have some fun with this. Maybe, if this will, there we go. Change for me. Did I go too many? I did. I advanced too far. Okay, here we go. Example 4. It says, determine which statement follows logically from the given statements. So we're looking for that P and R thing, okay? So, it says here, if you like musicals, so there's P. If you like musicals, then, And actually, let's stay consistent with our colors here. So I'm going to use P, I think was red. If you like musicals, then you enjoy theater productions. So the conclusion is, there you go. Okay, second statement says, if you are an actor, and so that is not, notice that we said that the conclusion of one statement should be the beginning of the next, the hypothesis of the next. And this is not about theater production, this is about being an actor. So this is actually going to be our R right here. And then our Q is over here. In other words, both statements have the conclusion in the same spot. You enjoy theater productions, you enjoy theater productions. That is not the right setup. It's supposed to be P to Q and then Q to R, not P to Q and then R to Q. Okay, so this does not work, and so it's asking us which of these statements is going to follow logically, and I can tell you right now that it's going to be D. Okay, because it's not in the right setup. Now, if it had been, if this second statement had been switched, then maybe you could conclude something. But in this case, there is no statement that follows logically because it's not in the right setup. All right. So then we have do-it-yourself number 4, and again you have two statements here. They want you to decide F, G, H, or I. And remember, look for the fact that you want 2 statements that have the conclusion of one, hypothesis of the other. Okay? So, and then we have our last example. And in this last example, we're kind of trying to put everything together. So it says, draw a valid conclusion from the given statements, if possible. Then it says, state whether your conclusion was drawn using the law of detachment or the law of syllogism. And in some cases, both. If no valid conclusion can be drawn, write no valid conclusion and explain why. Okay, so here we go. Given, if you are 16 years old, that's P, right? Then you can apply for a driver's license. That's Q. Okay, now remember that for this part, the first statement is very generic. Doesn't really say who that you are, but in the second statement, it clearly says this is not a conditional. That's the first hint. Okay, the law of syllogism requires 2 conditionals, 2 if-then statements. But the law of detachment only has 1 conditional and 1 that's not a conditional. So here you have a conditional, and this second part is not a conditional. So my guess right now is going to be that this is going to be law of detachment. But I want to confirm that, and if it is, P implies Q should be true, and then the next statement should be that P is true. Okay, it should be referring to P. So the question is Nate 16 years old? Yes, Nate is 16 years old because they're both talking about 16 years old. Then this is definitely a P statement. So we have P implies Q, and now we know that P is true. So now the logical conclusion that I can draw, and it is the right answer here, my conclusion, according to the law of detachment, is that Nate can apply for a driver's license. Nate can apply for a driver's license. All right? And my reasoning is that I'm using, or I'm supposed to explain what I used, I'm using the law of detachment here to make this conclusion. Alrighty? So that's pretty much how you do that. So here's example number 5. By the way, I was getting kind of tired of writing, so the directions for example 5 are the same as the directions for do-it-yourself number 5. Just a different example for you to try on your own. So I believe that, yep, if I'm not mistaken, this is the last example. So once you have completed this example, you will have completed your notes for this lesson, and I will see you in class, and thank you for watching.